So Brian Dutterer back today. We're doing lab number 9. The component that we're going to work on and actually finish up today, so when we get done today, our flywheel is going to be completed for assembling the engine. That is item number 10 in your part drawings. So you'll need to get that out and be able to look at it. The biggest thing that I'd like to cover is finding the location on the part where we want to drill and tap this 632 hole. And that UNC represents Unified National Course. You've heard those terms earlier in the lab series. We can see from the drawing that that 632 tapped hole goes through one side of this tubular section of the flywheel, but not through or into the other side. So we're going to want to pay attention to that. You've already done some threading, but the threading that you did is on the external of the stud, which is the component that screws into the top of the body and the cylinder swings back and forth on. But that was external threading, so what you used was a die. So you really needed to be concerned with the outside diameter of that component. Since we're going to drill and tap a hole, so a tap is what generates the threads inside of an existing hole, what I'm most concerned about is the drill diameter that I use to drill through so that it's ready to generate a tap. We've already went over in this series how to calculate what the major diameter of a 632 is. Typically, if I was using, say, a 1/4 20, the 1/4 inch diameter represents what the major diameter of that screw thread is. In this case, a 632 is definitely not a 6-inch diameter. It's very small. So that 6 represents a size. And those sizes were generated and made into standards well before I was on the planet. So we can go through real quickly how to calculate that major diameter, but I'm not going to spend a lot of time on it. What we do want to spend a fair amount of time on is how we're going to locate the part. So before we locate the part, we have to clamp the part in the vise. And I'm going to demonstrate that very quickly once we get down to the machine. It's going to take you seconds to fixture the part. So that's going to be a relatively easy step for you guys to accomplish. So let's not worry about clamping the part right now, but we do have a component or a tool that we've used previous to now. This is cylindrical, and you should know that this cylindrical component held together by a spring, and those two ground and lap surfaces allow it to run out of concentric. This part, or this tool, is called an edge finder. You should remember what that is, okay? Remember the name for it and how it's used. We know already, because we've used it before, that this major diameter of what I'll call the business end of that edge finder is 200 thousandths in diameter. The shank, which you hold in the drill chuck, and the larger body that is also a component of that 200 thousandths diameter, on all of the edge finders that you would buy for the machine shop that we specify, that diameter is going to be 3/8 of an inch. So 375 thousandths. Okay? You can buy them in different sizes, but for consistency, we try to use the same style and size edge finder for all of our students. Okay? So we have to figure out how we're going to use this tool to find 2 axes of location for the center line of that hole. So the first one is going to be in your front view, right? And this diameter is 1 inch in diameter. Now, if you used our material and it's just standard cold rolled stock, I would be willing to bet that for miles and miles of this material, if you took your dial calipers and measured the major diameter, that you'd be well within 1/1000th of an inch, okay? So I'm not going to worry about inspecting that diameter. If you want to quickly look at it and measure it before you do your edge finding, that's fine. But the major diameter of this part has a plus or minus 10/1000ths diameter. So we have to think, if it's plus or minus 10, which we should know at this point is a relatively loose tolerance, that the major diameter of this flywheel is really not that terribly important. If it measured 990 in diameter, or if it measured 1 inch 10/1000ths in diameter, it's really not going to affect how well this engine runs, okay, when we hook air to it. So let's just assume at this point that it's exactly as close to 1 inch diameter as what we can measure. And we're going to use this 200,000ths diameter on your edge finder to touch off on the outside diameter. Now when I do my touch off, what I need to be concerned about with that edge finder is that my 3/8 of an inch in diameter component, right? Not great to scale. That's better. I want to make sure that I'm touching, or I'm doing my kickoff, if you will, for that edge finder. The tip of this 200,000ths diameter has to be at and below the equator of the circle. Okay? That's step number one. Step number two, I want to make sure that this corner isn't what's hitting the 1 inch diameter. Okay? Because this thing's sitting there spinning. So if that corner hits that diameter, we've got a problem. Because if we hit somewhere up along above the equator, we have no real clue how big that cross section is. So we don't know how far we're going to step off. All right? Now as far as the tolerance to the center line of that hole, really the tolerance is set off of the center of the hole. So I've got a plus or minus 10 on this diameter. I would like to cut that in half because my half is going to be a radius measurement. That's 5/1000ths. I'd like to hold from the edge to the center line of the hole within 5/1000ths of an inch. That should be relatively easy for us to do. Okay? We have to think about how fast we're going to run that edge finder. When we had machines that actually ran faster, I would say 2,000 RPM and above. Well, what I'd like to do is, most machines you're going to run, while you're in our program, you're going to max the spindle out. Or try to stay in that 2,000 RPM range. Once you get on the mills on the other side of the wall, they'll run to 4,000 RPM. I'm not saying that they won't work, but because we don't buy the most expensive edge finders, that extra spindle speed could cause some damage to your edge finders. So let's stick around to 2,000. I believe the maximum spindle speed on our mills downstairs are around like the 1,400 to 1,600 RPM range. So that's where we're going to run that, okay? So I've started my machine and I've fed over nice and slowly so that I get an accurate edge finding. My edge finder kicks off. And now this cylinder, the 200,000ths diameter cylinder, is tangent to the edge of the 1 inch diameter circle. So it's pretty much as close as what your feel or how slowly or quickly you edge found. And I would suspect, and you're going to see when I demonstrate it, we're going to do it relatively slow so that we can hold a good tolerance on that edge. Easily within the 5/1000ths tolerance that I'd like to hold. Okay? Once I get that far, we have to know how far are we going to step over to get to the center line of the part. Well, if I've done my edge finding right, I don't care about the tangency of that 200 thousandths diameter. What I care about is the center line of the 200 thousandths diameter, or more importantly, the center line of the spindle. Because really the center line of the spindle is what we're trying to calibrate to the center of the part. So I do my edge finding, then I'm going to move over. I'm just going to write it down real quick. Edge find, so E, F, right? Do my edge finding. Number 2, retract the edge finder back up so I don't run into the part. Should be a pretty basic concept to think about, but I like to cover all my bases. Number 2, retract up. We won't write that down. Then we're going to step over, and we're going to call this the x-axis direction. Okay, so we're going to step over 0.1, and I'm going to put that at 0.100. You should have learned at this point, the more zeros that I put after the decimal point, or the more digits that I put, the tighter the tolerance needs to be held. Okay, because I said that I'd like to hold 5 thousandths to the center line, we would like to hold this dimension to 5 thousandths, and it just so happens that 3 decimal places is a standard 5 thousandths tolerance, plus or minus. Okay? So we've moved over half the edge finder, and then, next step, we're going to move over half of this diameter. So that diameter is 1 inch, so half of it is 0.5. Again, I'm going to hold that 500 thousandths well within the 5 thousandths tolerance. So if I just add those two together, we're moving over a total of 600 thousandths, right? Should be relatively easy. Now, at this point in the game, the center line of the spindle is lined up to the center line of the part. So we've accomplished one view, or one axis of location. So now we're going to turn over to our side. This is the way the side view. So if I stand beside the machine, looking at the profile of the part, I'm going to be moving in the y-axis direction. So in this component, we're looking at the y-axis and not the x, okay? So my y-axis here, I want to edge find, and quickly what I'll do is I'm going to remove these here in a second, just so that it's more clear where we're edge finding from. But we have to think about the location of that hole. Well, you may want to, at first look, with not a lot of experience, take 190 and subtract 75 thousandths from it so that I can edge find the front face. Wrong choice, okay? The reason it's a wrong choice is because this 190 dimension has a much bigger tolerance on it. It's got a plus or minus 10 thousandths tolerance. So if I choose to edge find off this front face, and I just do a simple subtraction of these two numbers, you might get lucky, but I'm not guaranteed that I'm going to be able to hold the tolerance for this 75 thousandths dimension. Okay? Because no matter what you do, you're not going to be able to make perfect parts. Now I have students come up and say, well, look, Mr. Bryan, I can't get this thing to read off 500 thousandths. That was what I was shooting for. Look how perfect that is. I can always come up with something, a measuring device, that's going to measure it more accurately and show you that it's not perfect. Okay? Surface finish, lots of things go into that. So what we want to do is we want to reference this front face. So we're going to ignore that dimension, right? We don't care about the 500 thousandths dimension. What we care about is edge finding off of that front face. We're going to put our edge finder up in this area, right? There's our edge finder. We'll start the machine up again at the max speed that our mills will go downstairs. We're going to start the machine up. We're going to take our y-axis, which is the handle right in front of me as I'm standing in front of the milling machine. I'm going to feed in until it just kicks off my edge finder. Again, nice and slow so I can control the accuracy. At that point, I'm going to reset my dial to 0. Now, resetting my dial to 0 is probably something I didn't go over here. But we can assume every time we edge find that we're going to set our dial to 0. Now, in a lot of cases, what I like to do is set my dial to 100 thousandths so that when I move the 100 thousandths for the edge finder, I'm already at a 0. Okay? So I move from 100 to 0 and then 500 thousandths more because one revolution of that hand wheel is 200 thousandths. Okay? So on this side, we've done our edge finding. Again, step number 1 for our y-axis position is edge finder. So I'm going to say EF. Step number 2. What would be my step number 2? Well, we can go back over to this procedure and we could say, okay, we're going to move over 100 thousandths. Well, if we move over 100 thousandths, the edge finder's center line is going to be in line with the face of the part. Well, okay, that might not be a terrible idea, but let's look at the procedure forward steps, okay? So we're 100 thousandths away. We need to be 75 thousandths away. So if we edge find, and step number 2, only move 0.025. That's the difference between the 100 thousandths radius and where we actually want to be, okay? Now we may have students that say, well, I moved in 100 and then I backed up 75. That puts me at the right position, right? The answer is absolutely not, because we have to start dealing with backlash. Backlash is a big problem. You guys have already been taught about backlash, but it's the slop or clearance between the nut and the screw that drive that axis to position. Okay? So if I change directions of the hand wheel, all I do is change from counterclockwise to clockwise. That slop has a certain tolerance to it, or a certain amount of gap. That we have to compensate for, so I have to come back plenty and then come back into 75 thousandths. Adds another step, adds a possibility that you're going to run into an error in the component, okay? And neither one of those things do we want to happen. So we're going to edge find, move in 25 thousandths. We're going the same direction that we edge found. If you change directions, number 1, you've taken out, or you've added backlash tolerance in, right? So there's an error. And then you move 25 or something less than 25 if you subtract out your edge find or your backlash. That's a problem. So let's look at it, okay? We're going to look at the position. Joe, myself, Jeff, we can look at it and say, oh, that's too far off. But we've made dozens of these things. This is probably your first time of doing this. So if you've got any question, get one of us. We're happy to take a look at it. So we've done our edge finding. We're not going to be putting a lot of cutting force in, but if you feel more comfortable, we can lock those axes in. Okay? If we lock the axis in, just remember to unlock them before you go to move the machine around again. Okay? So now that we've got our position done, that seemed like it took a lot of time, right? once you get in front of the machine, that position is something that you can do relatively quickly, okay? So now what I want to do is I want to go over step by step how I'm going to put the hole in. There's a couple of calculations or looking at information that we have to do. So now that we're sitting where we need to be, we have to decide what size hole we want to put in. Well, before we drill holes, what do we typically do? We typically do a center drilling operation. Remember, they're short and stiff. The tips are ground so that the center of the tool is relieved generously so that the zero rotation that a drill bit has is relieved as much as possible, okay? So it doesn't want to walk. So if I touch with a center drill, bring a drill back in behind it, it's going to stay in that position and just continue to drill, okay? What I'm going to look at, what we've used up to this point is a number 2 center drill. A number 2 center drill looks like this. Okay? Number 2 center drill, the major diameter or the shank diameter of the number 2 center drill is 3/16 of an inch. Well, I'm sitting 75 thousandths away from that wall. If I put the center drill in here and I drew it in, I'm going to find out that my center drill actually overhangs that shoulder. Because if I took 75 thousandths and I doubled it, that's 150 thousandths. That's theoretically the max size diameter that I can sneak down past this shoulder, right? Well, 150 thousandths is smaller than 3/16 or 187.5 thousandths. So that's number 2 center drill. When you get into the shop and you buy your tool kit, we have supplied, or we've gotten the toolkit set up now with a much smaller center drill. That smaller center drill is a number 1 center drill. The number 1 center drill's body is 125 thousandths in diameter, or 1/8 of an inch. Well, 125 is less than their 150 thousandths. So you can use that number 1 center drill to put that spot in, okay? So once we do our positioning, so number 1, position, okay? Number 2 step is going to be center drill, using a number 1 center drill. Okay, that's the tool that we're going to use. Now it's very tiny on the tip. I think a number 1 center drill has a 3/64 cutting diameter on the tip. It's very delicate. So all we're going to do is come down and just touch it. Okay? Now when we talked about drilling, we said, I had a really big drill bit that was relieved, and it was ground down so that the web of the drill bit is ground down to a point. That's called a split point drill. You should have that in your notes if you've watched this series. It's a split point drill. Well, what a split point drill does in production, we've already been through this, but I'll touch on it again. A split point drill alleviates the need for a center drill. It does a center drilling operation while it's drilling because it's all relieved at the tip, so it doesn't want to kind of walk around, okay? If I took my hand drill and I had a standard drill bit, I went to drill a hole, it's going to want to dance all around till it finds a place that it wants to drill into. A split point, put in a hand drill and I touch, it's going to start drilling right where it sits down. It's just a better way of drilling holes, a lot less cutting force. Cutting force reduced, heat reduced, okay? We use split point drills in this operation, but to teach you good practice, I would like to see you center drill. So we're going to use a split point drill, but we have to figure out what the tap drill size, or the drill size that is of the accurate size before we come in and tap the hole, okay? It needs to be smaller than the major diameter so that it leaves material in the hole for you to cut the threads, okay? So next we're going to move over to our decimal equivalent, or we call it our tap drill chart, and we'll select the drill size. So now we're ready to select our drill size for that 632 Unified National Coarse thread, okay? We've already stated that we care about the minor diameter, so we're going to pick out our tap drill size. In industry, we call it the tap drill size, okay? You should get used to hearing that. If you go into a machine shop, need a tap drill for a 632. On these decimal equivalent charts, if you look at the name of them, tap drill sizes and decimal equivalents. So up to an inch, it gives you all the fractional decimal equivalents, all the numbered size drill bit decimal equivalents, and then it jumps up to letter sizes, okay? 135 different pieces if you buy them from a tool sales place. What it does leave out is number 61 through number 80, but those things are so tiny that most folks never use those tiny little drill bits, okay? So let's worry about a 632. Well, if I look at the columns, and the columns are separated, the big columns, by red lines, I can see that my number series starts here. Odd 80, 164 and 172, 256, comma, 64. That means that there's two different variations of a number 2 thread size, okay? We get down here to number 6, and there's our 632. Again, the 6 does not represent 6 inches in diameter. It definitely doesn't represent 6 millimeters in diameter. That's not what we're dealing with, the metric system, okay? We're still in inch sizes. So a 632, and we're staying inside those red lines. 632, and I come over here, it looks like a number 36 drill is what I'd like to use for that tap drill size. If I go in my toolbox, and we've only got 7 different drill sizes that we give you to use for the lab, I'd still like you to pick up the drill. You can look on the outside diameter and see if it's stamped or etched the size diameter, and it would say 36. If it doesn't say that, we're going to take our calipers and measure the major diameter of that drill bit over the flutes, okay? If it measures something in the range of 106 and a half thousandths, then we know that we're good. If it doesn't measure exactly 106 and a half, is it the right size drill? Now, if it measures way big or way small, definitely it's not the right size. The calipers that you purchase in your toolkit are only accurate, I've seen them float several thousandths. So if I get something and I measure it, it's around 104, 103, might be 107, right? Somewhere in that range, it's likely the right diameter. If I really cared and I needed to make sure that the diameter was right, I'd get a different, either a nice set of calipers that I could trust that it was going to tell me the exact diameter, or I would go to using a micrometer. And I'm hopeful during the classroom session that you actually learn how to read and use a micrometer. It's not something we get you to buy because they are much more expensive. What we care about, again, don't care about the major diameter of the screw thread, care about that tap drill size. 632 is a number 36 drill, okay? Now we'll go back and look at our steps. So we've figured out that we need to use a number 36 drill, okay? That number 36 again is 106.5 if you're measuring with your calipers. How far do we want to drill? If I look on my drawing, it shows that I drill through one side, but not into or through the other side. No sweat, we can do that. But in both of these operations, the center drill and the number 36 drill, what do we have to do? We have to calculate the RPM. So we've already said in previous lectures that the formula is 4 times the cutting speed divided by the diameter of the tool, okay? If you're on a lathe, you're measuring the diameter of the workpiece because the workpiece spins. If you're on a milling machine or a drill press, we're going to calculate the diameter of the cutting tool because that's actually what does the spinning or the rotating, okay? A number 1 center drill we already said was 3/64, right? For what we're doing here, we're roughly around 50 thousandths. I'll round that up a little bit, okay? Roughly around 50 thousandths in diameter. That little tip, 4 times the cutting speed. The cutting speed for mild steel when you're cutting with a high-speed steel tool is 100, okay? That 100 is in the units of surface feet per minute. We're not worried about units. This is just straight through mathematics. You guys should be able to do this no sweat. 4 times cutting speed's 400 divided by 0.05. I don't even have to do the math, and I know that that's a really big number. It's actually such a big number that we can't reach the RPM that we calculate with the machines that we're using. So what are we going to do? We're going to max out the spindle speed. Again, the spindle speed on those machines is somewhere in the neighborhood of 14 to 1600 RPM. Okay? So on the center drill, max RPM. So I'm just going to say max RPM. I like to write things big enough that you can see it and you can copy my notes down. Number 36. When you've heard me teach in the past, when I'm doing these, I round things. As long as I round within 10%, I'm satisfied. So the diameter, 4 times the cutting speed, is 400, divided by 106.5 if you have a calculator, or you can divide it by 0.1. I like to round. Let's make it easy. Well, 0.1, there's 10 of those in 1 unit, right? So 10 times 400 is 4,000 RPM. We can't reach that RPM. Again, number 36 drill, max RPM. Okay? Use our cutting oil. We're going to drill down through to the inside of the hole. Okay? You'll see when we get to the machine that I position it in such a way that I can actually see in the hole while I'm drilling. So if you have any question as to whether you break through, you can look inside the hole and see the tip of the drill. Okay? Should be easy. You're going to get some resistance, then it break through. Whenever I do any cutting operation, what forms? Well, what forms is a burr, B-U-R-R, a burr. Well, there's going to be burrs up here on the top edge, and there'll be a burr inside the hole. Why do I bring that up? Well, it matters inside the hole because I still want that 3/16 shaft to slide nice and easy down through. So after we tap that hole, right? After we tap it, we're going to take our reamer and feed it back through the hole so that the shaft will run through, okay? And the shaft that runs into the flywheel is the shaft on the back of your crankshaft. You'll see that a lot clearer when we get to the machine, okay? So, number 4 operation is to tap 632. Well, this is our first time using a tap. When we used a threading die or a die on the lathe to cut the threads on the outside of the shaft, it should have been mentioned to you that geometrically on a die, if I look at the die itself, all it's got is cutting edges that shape that thread. There's no geometric feature on that die that forces it to cut good and straight. Well, if it doesn't force it to cut good and straight, then we have to make sure that we fixture it in such a way that it's forced to cut good and straight. Because if you start crooked, if I were to take a stud and put it in a vise and take the die and start doing this, the likelihood that it's straight to the center line is very slim. Well, if it starts crooked, it's going to finish crooked. You're going to have bad threads. The same thing exists with a tap. It's pointed on one end and you can see the thread, but just because it's pointed and it points down in the hole where I'm cutting the threads doesn't mean that it's going to cut straight into the hole, right? So if I start tapping the thread crooked, it's going to finish crooked. So we're going to constrain it. How do we constrain our center drill so it's parallel to the center line of the hole? We put it in our drill chuck. What about the drill bit? How did we constrain that to make sure it's where we want it to be? We put it in our drill chuck. What are we going to do with our tap? We're going to put it in our drill chuck. And because we want it to be good and easy to turn, we're likely going to release the belt tension so that you're not driving the motor while you're turning that spindle. And we'll go through all those steps once we get to the machine. But if we put the tap in the drill chuck, what is the last thing that we want to do? What is the last thing we never want to do with a tap in the drill chuck? As far as you guys are concerned, start the spindle. Do not start the spindle to put that thread in. I've had students that start it up and drill like they're drilling a hole. All it does is acts like a reamer. It makes that hole much bigger. That becomes a problem for us. So now we've got a part that's got a hole in it bigger than the set screw that we use to fasten it to the crankshaft. So we're going to have to take the part out, rotate it, reposition it to another side, right? And we're going to have to redo all these steps back to the edge finding. So if we do this right the first time, don't start the spindle. And we're going to twist. Once that tap gets positioned right over the hole, we're going to rotate the spindle, which rotates the tap, and hold pressure down on the quill. The quill is the body that telescopes in and out of the head, right? And as we rotate with quill pressure, it's going to feed down inside that hole. Now once it takes grip, and when I say takes grip, it needs to take grip 2 or 3 threads. Now we can take our hand off of the quill handle and turn the spindle. Again, with threading, tapping, or using a die, we want to make sure there's cutting oil there. We're going to rotate it and look down inside the hole. When the tip of the tap comes down and just barely touches the opposite side, this side down here, we're done. These are right-handed taps. So we're going to rotate it clockwise, that's a right-handed thread direction, as we're looking down from the spindle direction. Rotate it clockwise to go in, Once it just barely touches the other side, what do you think we're going to do? We're going to reverse the rotation counterclockwise. There's a spring inside that quill, so if I rotate it counterclockwise and I just hover my hand over the quill handle, as soon as it releases, it's going to take that quill handle and pop right back up in my hand. Okay? Once we get the thread out, or the tap out, we've generated the thread. You can look inside the hole, see our threads that are generated. That's where our 632 set screw is going to live. That part is almost done. Before we threaded, what did we say cutting operations generate? They generate burrs. So we got a couple different mechanisms here that we can use. Through the center hole, that hole was dimensioned at 1885 plus 1 minus nothing, right? That way it's clearance. We can get that 1885 reamer, spin it down inside the hole. We can do that after we take the part out of the machine because we're done holding that tolerance. Take ream down through, you can spin it by hand. Now a 3/16 pin will go down inside the hole. If you don't believe me, you can take your number 2 center drill and slide it in and out of that hole. It should slip through. If it didn't and your reamer cleaned up, you probably got the wrong size reamer. Okay? The other burrs that are going to be generated are going to be right up here on the top side. We have some emery cloth that you can use. We have some small files that you can use and just kind of file over the top edge. And in a lot of cases, it's such small burrs, I don't even deburr them for this lab. It's not terribly important. But if you want to get those burrs off, we've got some small files downstairs that you can get those off with. Now, at this point, it's done. Just to inspect it, we have a box downstairs on the workbench that's got some 632 set screws and a little 1/16 Allen wrench. Put your set screw in, make sure it feeds all the way in and comes out the other side of the hole. Make sure the nose of it pops out inside the hole. If it doesn't, you haven't tapped it deep enough. If you haven't tapped it deep enough, take your set screw back out. We've got a little tap handle that holds the tap. You can feed it back in the hole and tap a little bit deeper. Some people's we do have to fix, okay? But as long as you did all the operations right, but you didn't tap deep enough, we can fix that. So at this point, that part is done. Make sure you deburr and put it in your toolbox. Don't lose it. Okay, second part for lab number 9. We're going to work on item number 8, which we've already pressed onto the center shaft, right, for our crankshaft. So what we're going to do is put the hole in for the offset pin. Now if you remember back when we pressed this disc, item number 8, onto the shaft, we did our facing operations to make sure it was good and perpendicular to the center line of the shaft, and then we skimmed the outside diameter of this 5/8 inch diameter disc. Now why did we do that? Well, we did that because if for some reason the center hole is off center, and it very well could be depending on how good you press that disc onto the shaft, right? We want to make sure that the outside diameter runs concentric to the shaft that we pressed it on. So that way those two diameters are concentric. Well, why did we care about that? We cared about that because we're going to use that 5/8 inch diameter, which is slightly less than that now, to locate the center of the part. You might ask yourself, why is it important that we locate to the center accurately? Well, because the hole that we're going to put in has to be controlled to plus or minus 1/1000th of an inch. So plus or minus roughly 1/3 of the thickness of a sheet of notebook paper. That's pretty tight tolerance. Well, This isn't the hard part. I can dial over 188 thousandths and be well within a thousandth of an inch of how much I've dialed over. It's finding the center of the shaft and the disc assembly. So the rotating assembly, I have to find the center of that. Okay? Fixturing it, super simple. I'll show you that when we get down to the machine. We're going to use those plates that are in your gray toolbox, but everybody's been wondering what are they used for. That's our supplied toolbox that we give you. So we need to find the center. Well, you learned how to indicate the vise end straight, right? Well, indicating the vise end straight is something that you guys should be pretty good at now. You've done it several labs. You folks are kind of watching this through, but in a normal semester, you would be running the machines while this happens. So we're going to find the center of the rotating assembly using our dial indicator. Well, we're going to put our dial indicator in the spindle, and what we want to do is, as we rotate the spindle around, the tip of the dial indicator makes a shape. Well, what shape does it make? It makes a circle. So we want the circle that the spindle makes as it rotates to match the circle that's on the part. It's not terribly difficult. It's difficult for you to understand the first time or two. So we've got a couple different ways that we can show you how to find that center. First and foremost, we're going to roughly find the center by putting a center drill in your spindle, in your drill chuck, and move it over to the center of the shaft. We're just going to crank it over, use it like an Etch-a-Sketch. Everybody's familiar with one of those. We're going to move the handles around until the center line of the center drill lines up with the center of the rotating assembly. That gets us pretty close. Now we back up, we put our indicator in, and we'll find the center. That's all I'm going to say about that. Okay? Once we find the center, we have to take the backlash out, depending on the process that we use to find the center. Backlash is where all of this comes together. If we don't make sure that backlash is taken care of, no way in the world can we hold that thousandths of an inch. So let's just assume that magically we've taken care of backlash. We'll see that when we get to the machine. We move over 188 thousandths. If it makes you feel better, we'll lock the axes in so that it doesn't move around. So they're locked in position. We're actually sitting over where we want to put the hole in. What's the first step? Well, the first step after we position is going to be to center drill. Now on the flywheel, we used a number 1 center drill because it was much smaller. We had clearance issues that we had to work out. In this case, coming down from the top, I got all the clearance in the world. So I'm going to use my number 2 center drill. The tip on a number 2 center drill is a 1/16 of an inch in diameter. If I calculate my RPM, you guessed it, it's going to be higher than we can reach on the machine. So we're going to run at max spindle speed. Okay, run at max spindle speed. Number 2, we're going to put a hole in there. Well, it already tells us right here that the hole needs to be, when we're finished, 124.5 thousandths plus nothing minus a half. I could go as big as minus a thousandths and it would still press just plenty fine, okay? But these are the tolerances that we have to deal with. So can I expect that I can drill a hole with 124.5 thousandths diameter drill bit and expect that it give me a good hole so I can press a pin in there? You should definitely answer no, because there's 3 things that a drill bit doesn't necessarily do. Number 1, doesn't drill a round hole, right? Number 2, doesn't drill an extremely accurate hole. Number 3, it doesn't leave a really good finish on the inside of the hole. They're the 3 features that we care about. So what tool are we going to use to put that precision hole in? We're going to use a reamer. So we have to select our reamer. The reamer is going to be 124 thousandths because we're going to ream at the bottom side of the tolerance zone. So if it cuts a little bit too big, we're still well within tolerance. Okay? So we're going to use our 124 reamer, and we've got that in our toolbox. Remember to measure that thing before you use it. So 124 thousandths, how much undersize do we want to drill the hole? 8 to 10 thousandths when we're reaming a hole. So 8 to 10 thousandths means that I'm going to be somewhere in the 114 to 116 diameter. We're going to go over to our tap drill chart or our decimal equivalent chart and find out what size that is. So if I go over here to that size, right, we said 114 to 116, there's actually 116 thousandths diameter drill bit. And we see on the chart that that's a number 32 drill. That gives us the minus 8 to 10 thousandths size that we care about before we ream. So our next step is going to be drill through with a number 32 drill. We can do the math for our spindle speed. 400 divided by the diameter of that drill, which is 116. And if you look at it and do the math, you're going to be way faster than what we can reach on the machine. So we're going to run at max spindle speed. Cutting oil. Remember, cutting oil every time. After we drill through, we're going to ream the hole. Ream with a diameter of reamer 124 thousandths. Okay? Now we've learned that we have to do something with the RPM when we ream a hole. Okay? Well, these reamers have either 4 or 6 flutes. Typically, if you have a 4-flute reamer, which is twice as many as what the drill bit has, I'd cut the RPM in half. So if I calculate my RPM, divide by 2. On a 6-flute reamer, that's 3 times as many flutes as a drill bit. Chatter starts becoming a real problem. So I want to reduce the RPM. If I had 6 flutes, I'd like to reduce the RPM by a factor of 3. Well, these reamers are small enough that they only put 4 flutes on them. And those 4 flutes constrain it well enough to give me a good precision hole. So what I'd like to do is divide that diameter, right, or that RPM by 2. In this case, what I'm going to do is just lock in around 1,000 RPM. We found just with experience that the 1,000 RPM range works out pretty well. If I did the math actually works out that I could leave the RPM maxed. Okay? But for our purposes, I'd like to stick in the RPM range of about 1,000. It just works really well. It controls the size. So I'm going to say RPM approximately 1,000. Okay? So we're going to put that in the machine, set our RPM, ream through, and then come back up out. Shut your spindle off. You can take your workpiece out. Once you take your workpiece out, deburr the front and the back side. So you're going to use a countersink that's in your toolkit for the front side. The back side, the shaft's in the way. So you can use a combination between, I use a pocket knife and I kind of scrape it off, a little bit of emery cloth, maybe a file. I need to get the burrs off there. Then we're going to move over to our arbor press, our manual arbor press, pick up one of the dowel pins that are supplied to each student. Pick up a dowel pin. Number 1, I want to make sure it doesn't fall through the hole. If it falls through the hole, I want you to decide and tell me what happened. Well, 9 chances out of 10, you picked the wrong size reamer. So when I use the 124 reamer, I can look on the side, see if it's written on it. If it says 1260, it means it's the big size, it's the clearance size. It's not the reamer that we want to use. So we want to use the 124. If for some reason you ream it too big, we get to set it back up, find the center, step off in another location, and put another hole in it. Now your engine starts looking like Swiss cheese because you've got extra holes placed in your crankshaft assembly. Okay? We'd like to avoid from doing that. I'm going to show you on the arbor press how we press that pin in. Once you press the pin in, you're going to have something that actually appears to look like a crankshaft for a real little air motor. Okay? Only one operation. We're going to do that in the next lecture, is putting the flat on the side of the crankshaft, and then that component will be completely finished and ready for assembly. Okay, so that ties up item number 8. So here we are in the machine shop, and the component that we're going to work on first is going to be our flywheel. So we're going to finish that guy up here in pretty short order. The flywheel, the only requirement left on that is to put that 632 tapped hole. I told you when we were at the whiteboard that fixturing that guy, that part, is going to be relatively easy. And basically that's all we do. We set the small cylinder on top of the movable jaw in the vise, and we have clamps just the meaty section of the flywheel. I like doing that for the simple reason that I can see inside the hole. That way when I'm tapping, threading that hole, I can actually see where the tip of the tap is, because if I try to drive the tap too heavy a force, I could break the tap off inside the hole. Now we have a mechanism to get that out of there, but I prefer not to have to go through that process. So previous to that, we went ahead and indicated our vise end, so we're within our 2,000ths indicating of the fixed jaw. Remember, we only indicate the fixed jaw. So now we're ready to find the hole location. And here I've got my edge finder. I'm going to go ahead and put that in my keyless chuck. Keep in mind that we have to keep updating our spindle speed. The advantage with this component, when we're edge finding, center drilling, we all use the maximum spindle speed of the machine. And when we're threading, we don't actually turn the spindle on. Now I've previously checked and made sure that we were on our top set of belts or pulleys inside the motor compartment. Cover that guy back up. And we're going to be on forward high. If I go on forward high, that's where we're going to want to run. Go ahead and shut that off just so that it's a little quieter in here. So now I'm going to position that edge finder close to the outside diameter of that 1-inch cylinder that the flywheel's made from. So we're going to bring our edge finder down, and we want to make sure that the tip of that 200 thousandths diameter is at least at the equator of the circle. We want it to be at the equator or a touch lower. Now the tricky part becomes that we don't want that 3/8 of an inch diameter corner there to hit our cylinder when we're trying to edge find. Now you should be able to see from that perspective that I've got plenty of clearance, but let's go ahead and start the spindle up, and we'll come in and do an edge find. Now your perspective is not going to be the best one to see your edge finder kick out. You're going to be 90 degrees from where your perspective is. So we're gonna come nice and slow till it kicks out. And we wanna make sure that that 200 thousandths diameter is the only thing that's touching the 1-inch diameter cylinder. And it looks to be that's where we're at right now. So we're gonna set our dial to 0. Once we set our dial to 0, I'm going to go ahead and retract the quill back up. I'm going to move 100 thousandths. That's for half the diameter of the edge finder. And then we're going to move 500 thousandths more, which is 2.5 full turns. And we're going to finish up to be at 0 for you guys. And I lock the axis to the x-axis. Now we're going to bring the y-axis forward. We brought our y-axis forward. Bring our edge finder down so that that 200 thousandths, I'll call it the business end of our edge finder, is going to do our edge finding on this face, the front face of that 1-inch diameter cylinder. Like our edge finder to kick out a little bit so it's obvious when we get close. We'll come in nice and slow so that we can maintain our accuracy. And there we go, kick back out. Now that we've edge found the front, before we move the machine, I'd like to take a second to reset my 0. Now, I set my 0 to 100 thousandths because that's how far away from that face we actually are. Now, if we look back at our drawing represents that we have to be 75 thousandths away. So we're going to move from 100. Remember, we were turning this counterclockwise, so we're going to continue on to the 75 thousandths mark. Cutting forces aren't terribly high, but I'm going to lock my table in nice and securely. Take my edge finder out. Remember, our number 2 center drill is too large because of the clearance that we have up against this face of the flywheel. So we have a number 1 center drill, which the major diameter of a number 1 center drill is 1/8 of an inch. If you recall from our whiteboard conversation, we are allowed up to 150, so 125 is plenty small enough. So we're going to go ahead and reduce our chuck size down, and I'm going to hold on to my center drill. Notice I need to have enough sticking out. I have to have enough sticking out that I don't bottom out on this top surface. So if I have 3/8 of an inch sticking out, I should be plenty good. We can test and come down, make sure I've got the clearance. And we also kind of, when you have a little bit of experience, I'm kind of looking to see the distance just to make sure that I haven't made any mistakes. So we're in forward high position. We're going to take our cutting oil. I'm just going to put a little bit of oil right on that front face. And now we're going to take our quill and come down and just spot that surface. That'll give our drill bit enough of an indentation to take off from where that spot is. Now we're not going to go over our calculations or even looking at our tap drill size chart, but we wanted to use a number 36 drill for that 1032 tap drill size. I'm sorry, 632 tap drill size. So a number 36 is 106.5 thousandths. I'm reading that real close on the diameter. So now we're going to put that number 36 in. You'll get in the habit that you'll start measuring all your cutting tools before you put them in your machine, just to make sure You only have to mess up a part or two before you start double checking those diameters pretty regular. Again, max spindle speed. There's enough cutting oil still on there. So I'm going to come down and slowly drill through one side of that cylinder that sticks off my flywheel. So now I've got a hole all the way through. So now from this point forward, we're not going to run the spindle anymore. Take our drill out. This is our 632 tap. We can look on the outside diameter of it and see that it clearly says 6-32 UNC. There's actually a point ground on the end that you start feeding into the hole, and a cone or a point ground on the back side. Well, that front side cone, that little bit of a taper, kind of restricts my tap from going too terribly deep, because there's several threads that it takes in revolution for that tap to get up to the full thread form. Okay? We want to get the full thread form. Now, if the tip of that tap is going to give us any issues, we can just grind that off of there. There's nothing on that tip that the tap actually needs to generate that thread. That's actually there during the manufacturing process of the tap. And the only reason they don't take it off at the factory is because it takes more time, which would cost us more money. I'm going to open my chuck up a little bit. Bear with me getting that tap in there centered up. Lock my keyless chuck down. I'm going to put a little bit of cutting oil on it. And keep in mind, I want to hold pressure with my quill, or the quill handle, as I rotate the tap. And I believe we said during the lecture portion that one thing that you can do to keep you from applying too much pressure is we can loosen the motor up and just put slack in that belt. So now the only thing that I'm turning is the spindle itself. I'm not actually turning the belt and the motor and everything with it. So my cutting forces should be down, or my what feels to be cutting forces. Some of it's just drag. So if I bring that quill handle down, I'm going to put just a slight little bit of pressure on the quill. And notice I'm turning in a clockwise rotation. Add a little bit of oil. Once I get several revolutions in, then I can just turn the tap or turn the spindle until I see the tip of the tap just start to touch the other side, right? And then I can start backing it back off. So as you can see through that center hole, the very tip of that tap is touching the other side of the hole that it goes through. That's as deep as you want to go. If you try to drive the tap past that, you're going to start putting a lot of load on the threads and potentially cause that tap to break. So once I get that far, I'm going to turn the spindle in a reverse rotation, which is counterclockwise as I'm looking at the top. And when it frees up from the thread, it's going to release itself. Now that we've backed out the tap, we want to make sure that we have our component deburred. So at this point, we can open up our vise. So we open up the vise because there's really no other precision that we need to hold with location. So I've already pulled out my 1885 reamer. So I'm going to feed that inside the hole, and I can normally spin it by hand. Normally spin it by hand to clean up those burrs on the inside. Okay? So once we have those burrs cleaned out, if you'd like, you can go back and take some emery cloth across that top surface to get the burrs off the top. Now I don't get too ate up over the burrs across the top, because when it's assembled in the air engine, it's not actually a surface that you're going to be able to get your fingers to and potentially cut somebody. So at that point in the game, the only thing I would like to do is take my 3/16 or number 2 center drill and double check my slip fit and make sure that I have the clearance that I want. As long as I use the 1885 reamer, should not have any problem. So now we're going to move on to putting our offset pin in our crankshaft. Okay, so we're going to work on our crankshaft. This is our crankshaft here. We're going to put the offset hole that actually makes this a crankshaft. Okay, so we're going to hold on to that workpiece differently than what we've held on to a lot of pieces. So we here in the shop have actually made these plates. They kind of look like parallel plates, but not so much. They're not ground to as high of a precision as a parallel plate. But you can see that there's these grooves that are machined side to side. Those grooves are cut to a 3/32 radius. If you double that, that's a 3/16 of an inch diameter. Well, this crankshaft, the shaft part, is 3/16 of an inch in diameter. So if I lay that workpiece right in that groove, it gives me full support on the radius. Okay? The reason that I want to clamp on the radius is because if I were to just set it in the vise, I could definitely hold it that way, right? If I clamp the vise down, I could definitely hold it that way, but these are tool steel jaws. These tool steel jaws are heat treated, so they're actually harder than the hardness of the annealed tool steel shaft that we're going to clamp on. So what do you think would happen? You would likely compress it and put some little vise flats on the sides of that shaft. It's going to affect how good it runs. So if I put one plate opposing the other and I line up those circles or those radiuses that we have cut into it, right? There's our 3/16 diameter, and I put my workpiece down in one of those grooves and I clamp on it. That gives me good support, and it doesn't concentrate the pressure in any one place that's going to force it to have flats put on it. Now these plates were actually made when we had our old machines in here, so they're not quite high enough, okay? Because I'd like for that piece to kind of sit down in there, but I don't want to clamp on the 5/8 diameter either. You end up boogering that up. So what we're going to do is we're going to take our shortest size parallels, that's these 1/2 inch parallels, and I'll put one up against the fixed jaw or the back jaw, and I'll put one up against the front jaw. Now I'm going to put those plates in there. Once I get the plates in there, a little tricky one-handed. Make sure that those parallels go all the way across. So now I'm going to take that workpiece or the shaft for the crankshaft Make sure that those radiuses match up, because if they don't match up and you're clamping on the flat of the machine parallel or the machine supports that we've made, you're doing no different than if we just clamped into the heat treated jaws. So now from there, we'll go ahead and apply pressure with our vise, right? And now it's held nice and securely. There are times, and if I were going to machine this myself offline and not with students training underneath me, I may lift this cylinder or this disc up off the top of the jaws. Well, that causes a different issue. These two pieces are pressed together. So if while drilling I apply too much pressure on that 5/8 disc, I could easily dislodge that press fit and cause this piece to come off in two pieces. Now if I break this off into two pieces again, if that disc comes off the shaft, I get to at least remake that disc again. Hopefully I haven't boogered up the shaft enough, but I'd prefer not to have to go to the lathe again. So make sure that that is supported down on the top surface of these plates that we've machined. Another thing that I want you to take a look at is while clamped in position, there's a gap between those two plates. That gap actually measures just a touch over 1/8 of an inch. Well, 1/8 of an inch is very close to the diameter that we want to drill and ream through that disc, okay? So when we come down through, there's enough of a gap there that it clears the center drill, the drill, and the reamer. So we're actually going to center drill, and ream with our 124 reamer. So a 124 diameter, that gap between the plates measures something bigger than 124. We don't care exactly what that is. What we care about is that there's enough room that when I drill and ream down through, I'm not cutting on those plates. Some of the plates do have some machine marks in it, but typically that's from a student that has made an error. So now that we have it clamped into position, here's our number 2 center drill again. I'd like to put that up in my drill chuck. Put it in my drill chuck. I'll lock that keyless chuck down. And I'm going to bring my center drill down to the top surface of that crankshaft. Now why am I doing this? Because visually I would like to line it up as best as my sight can see, right? We center drilled the center of that shaft to relieve for my 1/4 inch counterbore. So I've got it centered up well enough at this point that now I can switch over to my dial indicator. And I want to center that up both in this direction and in the front to back direction, okay? And I feel like I'm pretty well centered up front to back as well. Sometimes the light gets to shining on and it's tough to see, but we'll fix that as we move forward in steps. Now I'll take my center drill out and keep that around because we're going to still need it. And I'm going to put my indicator together, right? Remember our stem, that swivel stem, goes on that dovetail on the back side. Of course I took it off, didn't I? I'm going to lock that dovetail in. So now that I have the dovetail locked in, let's go ahead and put that in my drill chuck. So remember, I have the ability to swivel this indicator wherever I want it. So now that I have it locked into position, I'm going to go ahead and swivel it down. You don't have to worry about looking at the face of it yet. I'm going to come around here, and I want to make sure that that little spherical ball is touching on the outside diameter of the 5/8 inch diameter disc, the component that's going to hold our offset pin. Okay, so now that the height seems right, I'm going to go ahead and apply pressure to my dial indicator tip. So what I want you to do is see that it swivels back and forth, and I want you to look at the dial. So I'm going to position it in such a way there's no pressure on that tip, so it's in a resting position. So now I'm going to apply pressure. Now this thing sometimes has a sticky spot. It's hard to get it to read. Where I want it, but I'd like it to read somewhere around 15 thousandths worth of engagement. Okay. So right there is my 0, okay? Took me a little bit of doing, and this ball socket section up here sometimes gets a little bit more pressure in there and it doesn't want to rotate freely. So I've roughly got from 15 to 0, so 15 thousandths worth of preload, if you will, on that indicator. So now my next step is going to be to rotate the spindle 180 degrees. Now it's going to be important for you to watch which direction that needle rotates. And you can see that it actually stopped moving, right? Well, it stopped moving because it actually came off of the workpiece. So we're going to go back. I'm going to make a little adjustment here. All I did was moved it about 5 thousandths. We're going to go back to the front side, and I'm going to put the preload back to 0. This is all part of the steps that you have to run through to get this thing indicated in. Okay? So now I've got 15 thousandths worth of preload again. I'm going to rotate the spindle 180 degrees. Notice that it's rotating counterclockwise, and now it's coming back. Now why is it coming back? Well, it's coming back because the front to back is actually out. So it's reading more of an elliptical shape. And as we get 180 degrees apart, my two readings are roughly within 1/1000th of an inch of each other. Well, because my position of that offset pin needs to be held to a tolerance of plus or minus 1/1000th, I need to make sure that I indicate this thing to way better than 1/1000th so that I can control that offset distance. So because my 0 and 180 degrees, if you will, are both matching at 0, I'm going to come back to the 6 o'clock position. My 6 o'clock position obviously doesn't match at 0. So I'm going to move my table. We're going to just run this machine like it's an Etch-a-Sketch, okay? Both handles moving, and I don't care about which direction I turn the dial. I just want to dial it in so it reads 0 all the way around, okay? Well, now that I've set my front, we should all agree that if I get 9 o'clock, 6 o'clock, and 3 o'clock all reading 0, and this is a circle, right? This little disc is a circle, that the fourth side should also read 0. But let's go ahead and go back to my 9 o'clock position. So now that we're at our 9 o'clock position, I'm reading pretty close to 0. Notice when I rotate the spindle around, I get a little bit of error, but I'm at 0. If I was off 0, I could reset my dial, right? Because this dial rotates, it would allow me to set it to 0 accurately. So now we're going to go back to 3 o'clock. So we're going to rotate this guy around. And I'm staying pretty close to 0, but it is going to shift a little bit on me. Now I'm roughly at 2 thousandths on the opposite side. So if I were to move it to where it reads 0, what's going to happen is it's going to be 2 thousandths off on the other side. And I could chase myself back and forth all day that way. Well, what I need to do is actually move it half of the displacement, because what we're doing is effectively changing it by its radius. So let's figure out which direction I need to move it to get it to read half of that 2 thousandths or 1 thousandths of an inch, and I'll reset my dial to 0. Okay? Small variations of this procedure don't cause any problems, but try to stick with the procedure as best you can. So now that we're at 3 o'clock, let's rotate back to 9. And that side reads within a couple of tenths of 0. So now we're going to repeat at the 6 o'clock position, and if it's off of 0, I'd like to adjust it and make it read 0. Okay? Now depending on the direction that I have to move it, I have to bring it into 0. Dictates which direction I need to run the hand wheel. And again, right at this point, I don't care about the backlash. So now I'm going to do a quick check at 9 o'clock, which I'm within a tenth or two of 0. We just changed the 6 o'clock position, so I'm right at 0. And we're going to look at the 3 o'clock position, and I'm within a couple of tenths of 0 on that side. And then we're going to switch around to the back side, which I think you can kind of take for granted that if I tell you it's going to read 0, that's what it is, okay? Because it's difficult for you to see with the camera. So I'm reading 0 on the back side within a couple of tenths, okay? So now this is the position where I have to take backlash out of the machine. And when I move off the distance, which I'd like to be off 188 thousandths plus or minus 1, I'm about as good as I'm going to get front to back. So I don't even worry about the front hand wheel taking backlash out, none of that mess. But 188 thousandths. I know that a lot of engineers like to talk about the right-hand rule, and the right-hand rule has a lot of value and merit. But at this stage of the game, what I'm going to refer to is counterclockwise and clockwise. Okay, that is enough information to get you through and position your machine spindle accurately over where the hole needs to be. So we're going to move counterclockwise where we're at right now and see that the needle has started to move off of 0. And now I'm going to come back clockwise. So if I say clockwise into 0, and I dial it as closely to 0 as possible, okay? And I only move 5 to 7 thousandths off of 0. These indicators have between 30 and 45 thousandths worth of travel. No way did I get anywhere near its limit, okay? So now that we've moved clockwise with this hand wheel, I'm going to unlock the hand wheel dial. Notice I'm not moving the hand dial. And I'm going to set my dial to 0. Okay? Now keep in mind that the last direction that I rotated this hand wheel was clockwise, so I'm going to continue going clockwise so I don't interrupt or I don't add backlash into it. Before I move off, I'm going to double check and make sure that I'm reading 0 all the way around that round stock. So I'm at 0. I was at 3 o'clock. I'm a couple tenths off on 6 o'clock. I'm around here to 9 o'clock. I'm a couple tenths off. If you want to fight over those couple of tenths, that's fine. It's just going to take you a little bit more time. And I'm going to just double check the backside, and I'm within a couple of tenths. So I've checked 180 or 360 degrees around, and I'm reading 0 with my dial indicator. Set my dial to 0. Last movement that I made was clockwise. Notice that I'm right at 0, off a little bit. Dial that in, and now we're going to move 188 thousandths, which is not quite one full revolution. 188 thousandths. Notice that my dial indicator tip is off of the outside diameter of that disc. I haven't moved my indicator. I could always go back in, go back to 0, and repeat that indication if I have any question, but I'm satisfied with where I'm at right now, okay? I moved the x-axis off, which is this direction, as opposed to this direction, because if I move the y-axis, I'm going to drill right into my parallels, okay? We don't want that to happen. So now that I've moved off in the x-axis, my 188 thousandths, take my indicator out. Okay, so now I have put my center drill in. I've already gotten into position, okay? We're going to put so little cutting force on the workpiece that I'm not worried about the table moving around. But if you'd like, you can just kind of lightly tighten up on that x-axis. The y-axis, if I were to bump that hand wheel, I'm going to need to go back and re-indicate that part in, okay? So my RPM, we've been calculating RPM plenty long enough at this point that I don't need to go through the calculations each time, but what you may see is me stepping over and changing RPM on the machines. But we are running at a high spindle speed. So my center drill's in. We'll go ahead and start the spindle. Again, with these center drills, I'm not worried about coming down more than just enough for the drill to be able to take off. Right? I'm going to come down. I don't know, 10 or 20 thousandths. Okay? So we've made a nice spot there for our drill bit. I'm going to take my drill bit. I want to double check that measurement because this drill needs to measure somewhere around 116 thousandths. And it's reading 117, which tells me that within the thousandths or so error that my dialing or my calipers have, it is the number 32 drill. Put that drill bit in. Same thing, RPM I've calculated. Spindle forward. We're going to come down. I think I'm going to reposition that quill handle so I can stay out of your way. And now we're going to drill that hole all the way through the workpiece. Okay? See how nice that drills? Drill the hole through. Stop the machine. Now I'm going to verify that I'm using my 124 reamer. I'm certain that you've been through the measurements of that reamer. So it appears that we've gotten in some 6-fluted reamers. That 124 size. So this reamer that I picked up, I believe is the 126 reamer, and it is. So I'm going to go back to my toolkit and pick out the 124 reamer. Now we're back to a 4-fluted reamer. I'm reading 124, so this is the right size reamer. You see the value in us double checking that measurement. We can also look at the outside diameter, but you'll find out as you get a little bit older like I am, it's tougher to read those numbers. Okay? I'm going to grab that reamer. I want to reduce my RPM because we said that we want to divide our calculated RPM by 2 or 3. So I'm going to get around the 1,000 RPM range. Let me walk through here real quick. I see on my chart that 1,000 RPM is step 2 on the pulley. 775 would be low range, which would be an acceptable place for me to be at. Let's go ahead and change this while I'm in the midst of it. Make sure you put that cover back on before you start the machine back up. And now in forward high. Now in forward high, we're running at 1,000 RPM. A little bit of cutting oil. I'm going to feed nice and steady down through. Once it breaks through down at the bottom of the hole, I'm going to pull it back up out. Okay? There's very little cutting force that you're going to run into with that operation. So now we've got our hole. If it turns out that we reamed with too large of a reamer, we're going to have to reset everything back up. Okay? So let's take our reamer back out. What I'm going to do is I'm going to countersink that hole while it's set up in the machine, because I do tend to have a little issue with holding on to things and countersinking them. Here's our back side of that crankshaft. That nice clean hole. Again, what I like to do, I might start out with this pocket knife to just kind of scrape that burr off. Once I get that far along, then I'll switch over to my emery paper, my emery cloth. I don't want to shoot that thing across the shop, so only because I know how much pressure I can apply to it, I'm just going to squeeze it ever so lightly so that it holds it well enough for me to be able to sand that backside. Okay? I I just want to make sure that there's no burrs sticking out the back side, okay? So now I've got that hole in there, and I'm going to meet you over at the arbor press so we can press that pin in. So here we are at the arbor press. You guys remember seeing this fixture once before, and what it does is it holds our crankshaft in a position that's perpendicular to this table, right, or parallel to the center line of the arbor press rack here, okay? So I've got that set in so that the top surface of my crankshaft is flush or close to flush to the top surface of that fixture. Now this is a new piece that you haven't seen before, but it's got a clearance hole for an 1/8 inch dowel pin drilled and reamed down through the center of it. And that hole is machined perpendicular to the face. So I'm going to pick up one of my dowel pins, and all they are is 1/8 inch diameter, 3/8 of an inch long. It's got a rounded end on it, and then it's got a tiny little chamfered end, and that chamfered end, depending on who you buy it from, become extremely short. Now because there's an interference fit between the hole that we reamed and this pin, I want this pin to go in really nice. I want it to go in without shaving a bunch of material, because if it shaves material, it's going to ruin or void the press fit that I'm shooting for. So what I like to do is I like to start down with the radius side down first. Okay, so that goes down in the hole first, because this chamfer on this pin especially is extremely short, and if it gets tilted just a little bit, it's going to shave material off the side of the inside of that hole. So what we're going to do is we're going to take that pin and we're going to feed it down through the plate. So you should see that, right? It starts coming out the other side. Once it comes out the other side, we can set it on top, and it's critical that that pin be lined up with the hole. Now, looking at this, even through the video, you can imagine that this rack center line, the pin center line, and then the center line of the stud on the crankshaft are all parallel to one another, okay? So if I bring this rack down and I touch the pin, now we're trying to press a tiny little pin in. Now this arbor press has roughly about 1.5 tons of push force if I grab way out here on the end of this handle. It should be obvious to you that I don't need that kind of intense pressure to press this pin in. So all I'm going to do is use this hand wheel that's on the side of my arbor press, and I'm just going to kind of steer it down in. So as I pull on it, it's going to press down in the hole, and I should be able to feel that, right? Until it stops. Now if you don't press it far enough, you may have to set it back up in the fixture. But what I'm looking for is when I flip that crankshaft around, that the face of that pin be flush with the back side. I don't see any metal shavings where it scraped the inside of the hole, and I felt good pressure as I was pushing it down in there. So now this should start looking more like a crankshaft to you. It's got that offset pin, and because of the way we controlled our setup, it should be good and parallel to the center line of the crankshaft. That's really the critical component. You'll see that as we get into the assembly process here in a couple of laps. But that takes care of this part.